quicker than the texture of space-time. Can stay aware of it and it'll simply tear, and I'm panicked by this presently. Our night sky is changing quickly, and in simply a question of many years, if not years, it could turn out to be totally unrecognizable. Cosmologists overall are sounding the alert. Specialists like Neil deGrasse Tyson have as of late affirmed the inescapable blast of Polaris, and the story behind it is very startling. Polaris, known as the North Star, has for some time been a constant in our night sky, filling in as a crucial reference point for stargazers, guides, and cosmologists. Anyway, this could before long change, adjusting our night sky and furthermore cosmic estimations. Let's dig into the meaning of this threat and its implications for us all. Join us as we uncover the tale of Polaris as it approaches its end. The role of Polaris. For quite a long time, Polaris has guided sailors and stargazers alike, standing firm on a worried footing as a guiding light. Its unfaltering presence in the night sky has been fundamental for navigation. However, this stability may soon be upset. In September 2023, a research paper presented by the respected Royal Astronomical Society cast doubt on the destiny of this divine illuminator. Polaris is near the very edge of detonating, possibly disappearing from the night sky forever. Before we investigate the results of this disclosure, let's see more about Polaris. Polaris, a unique star. Also known as the North Star or P-star, Polaris is unique because of its nearness to the celestial North Pole. Positioned nearly straight above Earth's North Pole, it appears almost fixed in the northern sky. Found in the constellation Ursa Minor or the Little Dipper, Polaris shines as a moderately radiant yellow-white supergiant star, a lot larger and brighter than our Sun. It's not a singular star but part of a complex triple star system, with Polaris A and Polaris B forming a binary pair. While Polaris B orbits around them, the interactions between these stars create gravitational forces that shape their orbits and influence their behavior. Any disturbances in these connections can lead to unpredictable variations in the star's brightness or pulsation patterns. However, the specific mechanisms behind these interactions remain unclear. Distance and light travel. Polaris is located about 323 light-years from Earth, meaning the light we see from it today began its journey over 300 years ago. Consequently, if Polaris were to detonate now, we wouldn't notice it until over 3 centuries later. The fact that Polaris has made it this far makes it even conceivable that it has already detonated and we are yet to witness the light from that event. Since ancient times, the North Star has held enormous cultural, navigational, and symbolic significance. Its stability and fixed position made it a valuable guide for ancient pilots, helping them navigate across oceans and lands. Symbolically, Polaris represented steadiness and direction, remaining steadfast amidst the ever-changing night sky. For astronomers, Polaris served as a crucial reference point, assisting in the study of celestial movements and variable stars. A crucial reference point. As a Cepheid variable star, its periodic variations in brightness have provided valuable insights into stellar properties and the nature of variable stars. This characteristic also played a crucial role in determining astronomical distances and aligning instruments. These pulsations follow a predictable pattern, which has been the standard for the star, making it easy for us to anticipate its behavior. However, recently Polaris has deviated from this normal behavior. This anomaly in its pulsation cycle has puzzled astronomers, leading to closer examination of this celestial anomaly. Rather than its typical predictable pattern, Polaris has begun to show inconsistent periods of dimming and brightening. Researchers are now raising concerns that the star might be approaching the end of its life. This lines up with behaviors commonly seen in stars nearing the end of their life cycle. The behavior of Polaris. The gradual lengthening of Polaris's pulsation period, which was once stable, can be attributed to interactions within its stellar system. We've noticed an annual increase in the pulsation period of 4 to 5 seconds, which might seem insignificant but holds serious implications. Some space experts suggest that gravitational interactions between the Polaris stars could be causing these changes in its environment, directly influencing its pulsation patterns. However, others are more alarmed, believing that the star is near the brink of detonating. The similarities between Polaris behavior and that of Betelgeuse, another prominent star in the Orion constellation, are striking. Both stars have shown astounding anomalies in their luminosity, raising concerns about potential explosions. Red giant stars in their twilight phase often show such inconsistencies before reaching the peak of their life cycles. While NASA has expressed heightened concern about Betelgeuse, similar attention has not yet been officially directed toward Polaris. The supernova question. As a red supergiant star approaches the end of its life cycle, it passes through various stages, including the main sequence, red giant stage, and finally the supernova explosion. Based on Polaris's unpredictable pulsations, researchers predict that it has entered the helium-burning phases typical of stars nearing their end. These anomalies in Polaris's behavior align with patterns indicative of supergiant stars in their twilight stages. However, definitive signs of its impending supernova remain uncertain. Astronomers are steadily analyzing these anomalies to understand Polaris's destiny. If Polaris were to go supernova, it would likely be a spectacular event in our sky, potentially outshining the moon and becoming one of the brightest objects visible for a long time, weeks or even months. Its appearance could dramatically alter the night sky, briefly modifying our perception of familiar constellations like the Big Dipper or Ursa Minor, of which Polaris is a part. Impact on Earth. Rest assured, Earth would almost certainly be completely safe, even if Polaris were to explode, given its mass and distance from us. While a Polaris explosion might not be as visually astounding as Betelgeuse's, it could still be visible to the naked eye for an extended period and eclipse nearby stars. Astronomers and observatories would undoubtedly take notice, sparking interest within the academic community and among stargazers worldwide. However, the specific visibility and impact on Earth's environment or atmospheric conditions would be less significant compared to a closer supernova event. What happens after a supernova? But what about Polaris itself? What will its fate be after a potential supernova event? Let's clarify one thing. While giant stars typically end their lives in a supernova explosion, this is unlikely to be the case with Polaris. When a massive star goes supernova, a tremendous explosion occurs within it, marking the final catastrophic stage in its life. This cycle involves a complete collapse of the core, triggering an immense shock wave that causes the star to explode violently. However, Polaris isn't large enough to undergo such an explosion. Instead, when Polaris exhausts its nuclear fuel, it will shed its outer layers and transform into a white dwarf. This change will not result in a supernova explosion, but rather a quiet end as it evolves into a small, incredibly dense celestial remnant. The white dwarf fate. A white dwarf is the remnant of a low or medium-mass star that has exhausted its nuclear fuel. It is incredibly dense, about as massive as the Sun but compressed to the size of Earth. When this happens, we will no longer be able to see its remnants from our planet in the same way we observe the star today. Comparing the expected impacts of Polaris explosion with historical supernova events provides valuable insights into the evolution of stars and their ultimate fates. Comparing our expectations with actual observations, such as SN 1987A and later events like SN 2011 Fe or SN 2014J, provides significant information for understanding the potential consequences of Polaris demise. Supernova remnants. SN 1354, for example, resulted in the formation of the Crab Nebula, a nebula that continues to grow and emit radiation across different wavelengths, offering astronomers a rich field for study. Similarly, SN 1987A, observed in the Large Magellanic Cloud, gave insights into the processes of nucleosynthesis and the properties of supernova remnants, for instance, the development of nebulae, the release of cosmic rays, and variations in brightness. These phenomena can offer insights into Polaris's unique characteristics. The formation of clouds like the Crab Nebula results from the expulsion of material during the supernova explosion, which interacts with surrounding interstellar gas and dust, enriching it with heavy elements and contributing to the process of stellar birth and death, cosmic rays, and stellar evolution. Additionally, the release of astronomical rays, high-energy particles accelerated by the supernova shockwave, has implications for astrophysical processes and cosmic radiation conditions. To make an authoritative comparison, researchers assess difference in mass, composition, and speed of expelled materials between Polaris expected burst and other observed events. This involves analyzing the light curves, spectra, and remnants from these events and projecting similar attributes for Polaris expected burst, evaluating whether Polaris explosion could lead to the formation of nebulae or particular elemental distributions. This enhances our understanding of its likely outcomes. Pulsations and instabilities. Another essential area of investigation involves assessing the pulsational behavior of stars approaching their end stages, such as Polaris, compared to observed supernova progenitors. This close examination can help verify similarities or deviations, providing insights into the explosion mechanism. Pulsational variation in stars nearing the end of their lives may indicate internal instabilities or impending catastrophic events, offering clues to the evolutionary processes leading up to supernova explosions. Despite careful observations and extensive analyses, astronomers remain puzzled by the anomalies observed in Polaris behavior. Unraveling the complex conditions driving these inconsistencies holds the key to better predicting when and how Polaris's fate will unfold, the fate of nearby stars and galactic impact. While the explosion of Polaris may not pose a direct threat to Earth, its aftermath could still have interesting consequences for nearby stars and even the Milky Way galaxy as a whole. Supernovae are one of the primary drivers of element formation in the universe. The catastrophic death of a star like Polaris, though not resulting in a full-scale supernova, would still expel a considerable amount of material into space, enriching the surrounding interstellar medium. This process is key in the creation of heavier elements, including those that make up planets and life itself. In fact, many of the elements in Earth's crust were once forged in the cores of long-dead stars. As Polaris sheds its outer layers and becomes a white dwarf, it will join the ranks of other stellar remnants scattered throughout the galaxy. Though a white dwarf does not have the dramatic flair of a supernova, its existence as a dense and stable object will contribute to the galactic population of dead stars. These remnants are particularly interesting because they serve as laboratories for studying the behavior of matter under extreme conditions. For example, astronomers have studied white dwarfs to understand the physics of electron degeneracy pressure, which prevents them from collapsing further. In the long term, even white dwarfs will eventually cool and fade, leaving behind only faint traces of their once luminous existence. The legacy of Polaris in human culture. Beyond its scientific significance, Polaris has also played an important role in human culture throughout history. As a fixed point in the sky, the North Star has long been a symbol of guidance and constancy. Its position has made it indispensable to travelers, navigators, and explorers who relied on its steady position to determine their bearings. In various cultures, Polaris has been woven into myths and legends, representing a symbol of hope or a guide through difficult times. For instance, in many Native American traditions, the North Star was viewed as a spiritual guide, leading souls to the afterlife. Similarly, in Western cultures, it has often been associated with leadership and stability. As modern navigation technologies like GPS have replaced the need for celestial navigation, the cultural importance of Polaris has diminished somewhat. However, its role as a symbol of constancy and orientation persists, and it remains an enduring figure in the imaginations of stargazers and astronomers alike. Astronomical research and the future of Polaris. Looking to the future, the study of Polaris will continue to provide crucial insights into the lives of stars, especially those in the final stages of their evolution. Ongoing advancements in telescopes, such as the James Webb Space Telescope, offer the possibility of more detailed observations, allowing astronomers to track Polaris's behavior with greater precision. This, in turn, could help refine our understanding of the fate of stars like it and even lead to the discovery of other similar objects that may be in the process of undergoing similar changes. Researchers are particularly interested in how the complex dynamics between the stars in the Polaris system might influence its ultimate fate. By studying the way these stars interact and how their gravitational pull affects their behavior, scientists may be able to predict more accurately when Polaris will reach the end of its life, offering a unique opportunity to witness the death of a star that has guided humanity for millennia. The role of Polaris in stellar evolution studies. Polaris plays a key role in the broader study of stellar evolution, particularly in understanding the life cycles of massive stars. As a Cepheid variable, Polaris's fluctuating brightness offers astronomers a natural laboratory for studying the mechanisms that govern pulsation in stars. Cepheids are pivotal to our understanding of distance measurement in the universe. By analyzing their pulsation periods and luminosity, astronomers can calculate the distances to far-off galaxies with remarkable precision. This method, known as the Cepheid variable distance ladder, has been crucial for measuring the scale of the universe.
However, as Polaris's behavior becomes more unpredictable, scientists are paying closer attention to its future as a way of refining our understanding of stellar dynamics. The insights gained from studying this particular star will help shape models that predict the outcomes of similar stars across the galaxy. This includes the behavior of other Cepheid variables in nearby star systems, which may provide further clues as to how stars of similar size and mass evolve and die. The long-term future of the night sky. While Polaris is unlikely to disappear in our lifetimes, its eventual transformation will be part of the natural course of cosmic evolution. Its eventual shift from a visible supergiant to a white dwarf will alter the appearance of the night sky, though the change will be gradual. In the distant future, after Polaris fades, new stars will take its place as the North Star. These stars, however, will be entirely different in composition and location. Astronomers predict that in around 26,000 years, the position of the North Pole will shift due to the precession of Earth's axis, and a different star, Vega, will take over as the northern pole star. This cosmic shift underscores the transient nature of the stars that have guided humanity. While our current understanding of the universe suggests that stars like Polaris may not explode in the dramatic fashion some might expect, their evolution still plays a critical role in the dynamic, ever-changing cosmos that surrounds us.